talking. All right. So section 33 is on more related rates. So it says sometimes related rates problems can get pretty tricky. So these next ones are going to be a little bit different than what we did before. So on a scale of 1 to 10, like where are you with related rates? Are you like at a 7? Like, yeah, this is okay? Or a 10? Like, these are easy? 5. Okay, so you're at a 5. So at the end of today, hopefully you'll be like at a 7 or 8 or 9. So we'll see. So you had this question on your homework. And I'm going to talk about why the answer that you have on your homework is probably wrong, because I didn't tell you one little tiny thing with this. So we're going to talk about it. So number 1, so it says 2 sides of a triangle have lengths of 12 meters and 15 meters. So imagine you have, a 12-meter stick, and then you have a 15-meter long stick. That would be a huge stick. Meters is really long. And then you can like rotate this. I don't know how to rotate this. So the angle between them is like smaller or larger. Does that make sense? So we can kind of rotate it around. So the angle between them is theta. So we don't know the side across from them, how long it is, because it depends on how big that angle is. If the angle is really, really big, then the side across from it's really large. Does that make sense? So what we're trying to do is we're going to be moving this angle at a rate of 2 degrees every single minute, and that's going to make that side across from it get bigger, which will also make the area of the triangle bigger, right? So that's going to be our formula. Our area is equal to 1/2 AB times sine of theta. All right. And in this case, we have fixed side lengths. Okay, so these are lengths of 15 and 12. So those are constants. Okay, so since we have 12 and 15 are constants, we can actually just plug them in. And I think in the video that you guys watched yesterday, I probably talked about this lady at a conference that was like really fired up about, I never teach my students to plug in constants. They should always do it with the product rule or whatever. So in this case, if you had 1/2 AB sine theta, you'd have to do like the product rule here multiplied by the product rule, which is really messy. And eventually we're going to do something called a trapezoidal trough, where there are variables B1, B2, H, L. There's 4 variables, and it would be really annoying. So this is why I'm a nice calculus teacher, right? And I let you plug things in. So you can plug in constants only if they are indeed constant, right? So 12 and 15 are constants. So that means if I did take the derivative of them, so like the derivative of side A, derivative of side B, they would be 0. They're not changing. There's no rate of change for them. So as I multiply that out, I get 90 times sine of theta. And as I take the derivative, I get dA over dt equals, and the derivative of 90 sine theta is 90 cosine theta. But since we took the derivative of theta, d theta over dt, right? And we can start plugging things in. So we know that d theta over dt is 2 degrees per minute. But this is the thing that I didn't tell you before. So imagine you went ahead and you multiplied this all out. In physics, you always have to keep your units in the problem. Is that right? Does Mr. Crawley make you keep units in the problem? Yeah. In most science classes, you have to keep your units throughout. So in calculus, I'm kind of lazy with that. We just kind of do numbers, and then we get the unit at the end. We can think about it, right? So if it's going to be area, it would be like meters squared per minute, right? If you kept the units in throughout this problem, and this was in degrees per minute, and this 90, what do you think 90, because it came from the 12 and 15, what are its units? Meters. Meters times meters, right? Meters squared, and then cosine ends up being a number. Trig ratios are always numbers. Like when you guys learned SOHCAHTOA, sine equals opposite over hypotenuse. Sine of theta is always just like 4/5 or 1/2, right? They're all like just numbers in the end. That's a number. So if you took meters squared multiplied by a number multiplied by degrees per minute, what are our units?
Meters, degrees per minute.
Meters squared, degrees per minute. Isn't that weird?
So you have to get rid of the...
Yeah, we have to get rid of the degrees somehow. Okay, radians is the way that we get rid of the degree. So I told you every single thing in calculus is in radians, okay? There's a reason that we use radians a lot. So basically, radians is a non-unit. It is a made-up unit. We just came up with it. So radians, instead of saying like radians per minute, it's really just per minute. There's nothing there. Radians is like an arc length, but like what's the length? I don't know. Is it in meters? Is it in second? Or not meters? Is it in feet? I don't know. We don't know what it's in. So radians is a made-up unit. Okay? So we want this to be not degrees, but we want it to be radians per minute. So So we need radians per minute, which is really just nothing per minute. Okay. So we do that. So we do 2 degrees per minute. Well, 2 degrees per minute is the same as, how do I convert degrees and radians? Those of you that are helping pre-calc people right now, you might know. Yeah, it's pi over 180. Have you had pre-calc students asking you questions?
Yeah.
So you get 2 over 180, which is pi over 90. So that's going to be our radians per minute. So as I plug in, I get d over dt equals 90 times whatever cosine of theta is. Well, we have cosine of 60 degrees. We could change that to radians.
But it's just going to be a number.
Yeah, it's still just going to be a number anyway. So like the part in there, like the cosine of 60 versus cosine of pi over 3, those are the same thing. So if you want to write 60 degrees, I don't care. And then times pi over 90. So the 90s reduce out, and then you guys just told me that the cosine of 60 is 1/2. So our answer is pi over 2, exactly. So d over dt equals pi over 2, and now it is in meters squared per minute, which is what we want. It's not meter squared radians per minute. Radians we can just leave off. We don't have to say radians. It's kind of like, you guys remember when we do like 180 degrees is the same as pi, right? We don't have to say radians there. So 2 pi is the same as 360, right? Okay, so that should be the answer. So you don't have to fix the one on your homework. It's fine. I just won't. It's fine. I mean, for your own reference, maybe like put something there. All right, number 2. So a balloon rises at a rate of 3 meters per second from a point on the ground 30 meters from an observer. Okay, so we're 30 meters away, and here's the observer, and then here's the balloon, which is going up. So we have a y and we have an x. X is constant. Y changes. Y is getting bigger, right? So it's positive. And the y is going up at 3 meters per second. So that's my dy over dt equals 3. So we want to find the rate of change of the angle of elevation. So as the balloon goes up, this angle is getting larger. So, you know, you guys had your homework for related rates day 1, and you did a lot of things with the Pythagorean theorem, which is fine, but it seems like every time I put a question like this on the test, wink, there's always students that try to set it up like x squared plus y squared equals z squared. And what are they missing when they're doing that? The theta. We need that theta, right? That's what we're trying to find. We're trying to find how quickly the angle of elevation changes, right? We need a theta. So we actually need an equation that relates theta and then y and x. Okay. So if we look at it, we have tangent of theta is equal to opposite over adjacent, right? And that adjacent is actually just 30. So I can plug in 30 for x because it's a constant. So that's really like 1 over 30y. So it's really easy to take the derivative of that. What's the derivative of 1 over 30y? 1 over 30 dy over dt. But tangent, a little bit harder. Some of you guys might have gotten this on your derivatives drill. I hope so.
Secant squared theta.
It's secant squared theta, and then it's d theta over dt.
I already forgot it.
Well, you can always get it by doing the quotient rule of sine over
There you go.
cosine. It's just on the AP test, you will run out of time, just like you ran out of time on the derivatives drill. I know, because I gave you an extra 10 seconds, right? All right, so we start plugging things in, and we know the dy over dt. We're like, okay, that's 3. We're trying to find d theta over dt, and then we're stuck, and we're like, wait, what's secant squared theta? So we don't know. So usually in these problems, and even in the ones that did involve the Pythagorean theorem, like the latter problems, we kind of redraw. So we're like, well, at this exact moment, the person was 30 meters away, and we said, find the angle of elevation when the balloon is 30 meters above the ground. So if this is 30 as well, what is our angle? 45 degrees, right? Because we have an isosceles right triangle. Okay, and then you could plug in secant squared theta. You could find it that way. Or sometimes it's easier, especially when you don't have a nice one like this where it's like 30 and 30. Like if you had something like 4 and 5, okay, it's much easier to do the way I'm going to show you. So if you want secant of theta, it's just 1 over cosine. It's going to be the hypotenuse over the adjacent, right? So then secant of theta ends up being 30 over 30. Not 30 over 30. What am I talking about? 30 root 2 over 30. How did I get the root 2? Yeah, the 45, 45, 90 triangle. Do you guys remember how it's n, n, and n root 2? Yeah. And then so that ends up being root 2. So then you can go directly in here and just replace the entire secant theta with root 2 instead of doing like secant of 45, like secant of 45, and going through that process. You get the same thing in the end. Okay, so I have square root of 2 squared d theta over dt, and then this becomes 1 over 10. So when I divide the 2 over, I think I get 1 over 20. So this is in, I don't know, what are the units? It's a non-unit, right? If you check all of your units as you go through the problem, this was just a number. Your 1 over 30, this was something with meters. No, it would be radians per second. That would be the answer. Nope. I would just leave it like that. That's your answer. So if you have a like there was no place where I like gained a degree, right? Did you see anything where I was like, I had a degree anywhere? No. So if it's just like a number per second, then it's radians per second. Like a number per second, they would need radians per second. All right, this one's kind of a weird situation, kind of like the ladder problems. Okay, so this one says a construction worker pulls a 5-meter plank up the side of a building under construction by means of a rope tied to one end of a plank. This seems so incredibly dangerous. Every year I do this problem, I'm like, why would someone do that? Like just hanging over the side, like, ooh. All right, there's probably some kind of pulley or something that's helping with this. But so the worker pulls the rope at a rate of 0.15 meters per second. How fast is the end of the plank sliding along the ground when it's 2.5 meters from the wall of the building? So do you guys see what's happening? I'm going to call this x and this y. And I have a right triangle. I have x squared plus y squared equals 5 squared, right?
So why not just 1 plus 4?
No, because it could be anything. I don't know.
Oh, it's 5 squared.
Okay, so we have this right triangle that's being formed. And I have this drawing here. So that says 0.15 meters per second. Okay, think about this. Is this blue line getting bigger? No, it's actually getting smaller by 0.15 meters per second. But that's not the part in my triangle, right? Are we looking at the triangle? This y is getting bigger. The y is increasing by 0.15 meters per second. So this is our dy over dt. So we take the derivative and we get 2x dx over dt plus 2y dy over dt equals 0. And we can divide by 2 if you want to just get rid of the 2's. Right, I do that a lot on these Pythagorean theorem ones. And then we start plugging in. So we're like, well, we want to find how fast is the end of the plank sliding along the ground. So we want to find dx over dt when x is 2.5 meters from the wall. Yeah, so 2.5, and then we don't know dx over dt. We know dy over dt, but what about y?
No, we don't.
Yeah, so this is where we redraw the triangle like we did on that last one. And we're like, oh, well, at that point in time, we have 2.5, and we know this is 5. Yeah, it actually is a 30, 60, 90. You could do 30, 60, 90. So it ends up being like 2.5 root 3 on this. Or you could do your Pythagorean theorem and just write it as a decimal. So 5 squared minus 2.5 squared. Yep. It's 4.330. So I'm going to put that here. So 4.330. So y is equal to 4.330. Do I need to write out the Pythagorean theorem? You guys see that? Yeah.
Why can you cross out the 2's?
Because it's just like you're dividing by 2 everywhere. So dividing the 0 by 2, it's still just 0. Okay, so now you take that number in your calculator, multiply by 0.15, subtract it over, and then divide by 2.5. So if you do all those steps to solve for dx over dt, you get negative 0.260. Whoops, that's a 6.
1.2. I got 2 points.
Negative 0.2598 something.
Wait.
Yeah.
No.
Okay, so check it again. Yeah, it's 0.15, not 0.015, right? So do 0.15.
Oh, I did.
Your range should always be negative for these types of problems.
Well, you should always think about what's happening here. So he said, should the answer always be negative? In this case, we're trying to find how long or how the distance, like how x is changing. Is x getting bigger or smaller as this gets pulled up? This distance gets smaller, so it should be a negative. And so then Ari was asking yesterday, he said, you know, like when you phrase this, if it's negative, could you be like, it's increasing at a negative rate? And I was like, that's weird. Like, don't do that. I would say it is changing. So the distance, like x is changing at a rate of negative 0.260. Did you do that on your homework? Annoying. I should count all of them wrong.
It sounds
Alright.
like, but it's saying how fast is it going? Are you saying like along the x-axis at 1?
Yeah, it's like sliding closer to that.
Oh, okay. I thought you were talking like no matter what direction it was going, how fast it was going.
Yeah, it's just sliding closer to the wall. That means that you're losing like 0.26 meters every single second.
Oh, because I thought it meant like
Could you
you're
say
in a car backing up, you're still going. Whether you're going forward
Like the
or backward,
speed.
you're still going.
Yeah.
You're not really going.
No, this is talking about losing distances or gaining distances and volumes and so on. Okay, so the next one. So gravel is being dumped from a conveyor belt at a rate of 30 cubic feet per minute, and its coarseness is such that it forms a pile in the shape of a cone whose base diameter and height are always equal. Well, isn't that convenient? I don't think that's how like conveyor belt and like coarseness of sand works. Like I think it would, yeah. I know. I think that probably it would get like wider faster than up, but who knows? All right. So anyway, so we have this. So the volume of a cone is 1/3 pi r squared h. And as we could take the derivative here, but if we took the derivative here, we would need to do the product rule, which is fine. Like Mrs. Hogan asked me one about this the other day. She had done like the product rule, and then I was like, oh, actually, you can use like similar triangles, and that helps. She was like, oh yeah, I forgot about that. So if you can do that, it makes it a lot easier on you. Okay. So if you have d is equal to h, well, d is 2r. So I can replace all of my r's with h's over 2s, or I can replace all of my h's with 2r. It says that the diameter and height are always equal in this case. Yeah, exactly. You want to think about what it's looking for. So our question says, how fast is the height of the pile increasing? So we want to find dh over dt when the pile is 10 feet high. H is equal to 10. And sometimes I trick you. Sometimes I'm like, find dh over dt when r is equal to whatever, or when diameter is equal to whatever. In that case, it doesn't matter which one you solve for. But to make it easier on us in this situation, I would get everything in terms of h, right? Because we want h's. But if I messed up, and did you guys see me do that on that video too? Like sometimes I mess up and I just start going through my problem and I don't think about it. And there was one that involved surface area of a sphere. And it asked for the change in the diameter. And I got the change in r, right?
Really?
Well, that's okay. You relate the two. You're like, oh, well, my r is equal, if I do 2r, that's equal to d, and then you can take the derivative from there. So any equation that you get that relates those two derivatives, you can use. So if you mess up, don't just erase everything. Like a lot of times people are just like, oh no, I got h instead of r, and then they like cross out the whole thing. Like, oh, you're almost there. Like just change it. Okay, so anyway, so we're gonna solve, we're gonna replace all of the r's with h over 2. And then another thing students do here is now they take the derivative and they still have to use the product rule. Like we just want to simplify as much as possible, right? I'm like a broken record. I say these things every year and still people do them. So if I simplified all this, it ends up being pi over 12 h cubed. Can you see that? Because the 2 is going to be squared to give me 4 times the 3. So now I can take the derivative. So dv over dt is equal to, so when I was in school, I just wrote the pi over 12 and then I took the derivative of h cubed. That's fine. So the derivative of h cubed is 3h squared dh over dt. Or you could do it all together. So some of you guys might have pi over 4 h squared dh over dt, which is fine. Still with me? And we start plugging in. So we look for clues. Notice how this says 30 cubic feet per minute. That's our dv over dt. Oops, of course I just moved that. right? That's a volume, cubic feet, right? We look for our clues like that. So that's 30 here, and it's growing, right? So it's positive 30, not negative 30. And then I have pi over 4, and I want to know my h. Well, I said when, at that point of time, when h is equal to 10. And then I find my dh over dt. So I take my 30, I multiply the 4 over, I divide by 100. Whatever, it doesn't matter. So we get 6 over 5 equals pi times dh over dt. Is this coming from Maury's room now too? I got music on both sides now. All right, and then I divide by pi, so you should get 6 over 5 pi. And sometimes it's just the simple things, guys.
Yes.
Some of you guys make simple little mistakes. So then you would put this into your calculator and you would forget that the 5 pi, like the pi's on the denominator. So if you put this in your calculator, I would do parentheses unless you have the fancy font that shows you the numerator and denominator. So this answer should be 0.382 feet per minute because it's a height or it's a distance, right? It's not like an area or a volume.
Could you say that it is increasing at a negative 3.2?
If you would like to piss off the AP graders, you go for it.
Technically, is that right? Would that be counted?
I mean, I think I would count every single point that I could for someone that did that. I would not give them their points. I'd be like, this person's annoying. All right, we're going to skip the trough one, and we're going to go to number 6. I'll do the trough on Monday. All right, so water is leaking out of an inverted conical tank. So when you have an inverted cone,
No, it's just upside down.
yes, it's an upside-down cone, and you see a lot of calculus questions like this. And there's a reason that there's a lot of calculus questions like this, because we use a lot of these. These are called funnels. Do you guys know what a funnel looks like? Funnels are everywhere in the world. So if you think about, do you guys know what a grain silo looks like?
Yeah.
Okay, so if you have a grain silo, at the bottom of it, there's a little cone. It's actually much smaller than that. You can't really see it very well. So if you look at them closely, there's like this little cone down there. Okay, and then you can drive your truck underneath, and you can fill it up with grain. That's how they work. Okay, I know, your mind is blown. All of you city folk have no idea what I'm talking about. So, all right. Maybe. Find the related rate. Okay, so we have water or whatever is leaking. So this in this case it's water. So it's leaking out of this funnel at a rate of 6,000 cubic centimeters per minute at the same time that water is being pumped into it. Okay, I know this can be overwhelming. The first time I saw this problem, it was overwhelming for me. I was like, oh, there's too many numbers. Okay, so here's the easiest thing to do. So identify what we have. So the height is 600. And the diameter is conveniently 600 as well. Which means when we talk about the radius versus the height of the water, right, we get the radius over the height of the water is equal to 300 over 600. In other words, the radius is always, 2r is always equal to h, right? Does it make sense? The diameter is always equal to the height of the water. You with me? Kind of the same situation as that coarseness of the grain problem we just did. All right, and all we're going to do is we're just going to think about the change in volume altogether. I'm not going to worry about what's coming in, what's coming out until the very end, okay? So we know that the water level is rising at 29 centimeters per minute, and we want to find the rate at which the water is being pumped into the tank. So we want to find, I'm just going to find generic dV over dt when h is equal to 150. But when I talk about the volume, the total volume is the volume of what's coming in minus the volume of what's coming out, right? So what I'm going to write is that the rate of change of the volume is actually, it has to do with what's coming in minus what's going out. Okay, and I know that's probably like weird for you right now, so let me give you easier numbers. Okay, in this problem, the water is going up still. The height is increasing, right? Is the water coming in faster than the water coming out, or is the water coming out faster than the water coming in? The in is faster than what's coming out. Does it make sense? That's the only way that the water can rise. Okay, so what we need to do then is if I had like 500 coming in and 100 going out for volume, what's my total change in volume? 400. Does that make sense? That's what we're doing. We're doing like 500 minus 100, right? So we're going to get our total change. But we're not going to worry about that part till the very end. So we're going to do our volume equation is still 1/3 pi r squared h. And our r is going to be replaced with h over 2, still, just like that last one. So it ends up being that pi over 12 h cubed that we had before. I'm going kind of quickly because we just did one just like this. So dv over dt then is pi over 4 h squared dh over dt. Everybody with me? So we start plugging things in. So I get pi over 4, h is 150, dh over dt is 29, dv over dt is what we're finding. And we get an obnoxiously large number. I did. So we get 163,125 pi. So you could multiply the pi in if you want, I don't care. Which is approximately 512,472.302. It is in centimeters. And if it's like a silo or something, makes sense that it'd be a lot. All right. So now the question is, well, what is the rate at which the water is being pumped into the tank? That's the total change in volume. That's the 512,472.302 number. And we know that the amount of water coming out is 6,000. So what do? I add 6,000 to it, which should make sense because we're undoing what's leaving the tank, right? So our answer, our amount coming in, is 518,472.302 centimeters cubed per minute. Hours? What do we got? Minutes. I didn't want to scroll back up. All right, there we go.
In kilometers per hour.
Yeah, you could convert it. All right, so are these making sense? All right, so let's look at the homework problems. And like I said, we'll skip that trapezoidal trough. Remind me on Monday to